All right, calculus. We're on day 5 of Unit 1, and we're going to take a slight detour today by looking at limits of functions. So we've been looking at limits as finding the slope of the tangent by taking smaller and smaller intervals of the secant. So in the limit, as that interval gets so tiny and approaches 0, we get the tangent slope. Today, we're going to take the limits of functions as we approach a certain x value. What does that function approach? So a slightly different thinking on a similar theme. So for the graph that you have in front of you, which might be on the wrong page in your handout, but we have this cubic, and we want to look at what happens as x approaches the value of 3. Sorry, I was deciding what I was looking for. So I am looking at this function as we get closer and closer to the x value of 3. What is happening to the function? So the limit as x approaches 3. What happens to our function? Well, it approaches a value. It's defined where x is 3. It has no gaps. It is approaching, for what it looks like, a value of -2. So the limit as x approaches 3 of the function is -2. We're getting closer and closer to that value as we come from the left and from the right. Sometimes it can be helpful to trace along with your fingers. What value are we approaching from both directions? So that in the limit, as we get closer and closer, we approach that value. For the second one here, b, we have a quadratic. And I want to know what's happening as x approaches -2. So as x gets closer and closer to -2, what's going on? Well, it looks like I'm approaching a value of 0 as I come from the left, and it looks like I'm approaching a value of 0 as I come from the right. So the limit for that function as x gets closer and closer to -2 approaches a value of 0. We can say the limit equals 0 as we get closer and closer. This function, a little harder to see, but I want to know what's happening as x value approaches 0. So for my function, I'm getting closer and closer to x equals 0 coming from this way, and I'm getting closer and closer to x equals 0 coming from that way, and we're approaching different values. Uh-oh. There is no limit. Okay, this is how we would write it. The limit as x approaches 0 from the right side appears to be getting closer and closer to that y value of 1. But as I approach that x value of 0 from the left side, the function appears to be approaching a value of 2. Those two values are not the same. There is no limit. The function is also undefined there. There are holes. This last one, an absolute value function. We want to know what's going on as x approaches -1. As I come from the right-hand side, I'm getting closer and closer to a value of 0. As I approach from the left-hand side for the function, I am getting closer and oh, I'm sorry, I just lied to you right there. I am getting closer and closer to a value of -3. And as I come from the left-hand side, I am getting closer and closer to a value of -3. So the limit of this function, it is approaching the same value from the left side and the right side. And you would probably know that there is not a tangent at that point. It's a totally different thinking. The limit of the function is -3 because it approaches the same value from both sides. Algebraically, let's look at f at x equals x squared minus 1. We know from our transformational thinking that that's a quadratic that's down 1, so we know what it looks like. We know that it is continuous and defined for all values of x, and so that I'm expecting my limit to be defined as I come from the left and from the right. So I have a continuous graph. As I am approaching from the left and from the right, my value exists. At x equals 2, and I can see I am approaching that value in both directions. F at 2 equals 2 squared minus 1, which is 3. F at 2 is 3. For the next one, I have f at x equals x squared minus 1 over x minus 1. I know that I have a problem, either an asymptote or a hole. To determine which, I see if the bottom is divisible into the top. Since this one is a difference of squares, I can see that visually it's going to look like x plus 1, where x cannot be 1. So I know that I have a hole. I do not have an asymptote. It looks like a line with a problem. Oh man. Okay, you draw yours straight, please. That's just crazy. The graph is not continuous. It is not defined at x equals 1. But you can probably see that there is a limit if we come from the right or from the left. We are going to be approaching the same value. Lastly, we're looking at a piecewise function. Let's draw it. So I'm going to do the easiest first. The value of the function is 1 when x equals 1. The value of the function is a line with a y-intercept -1 when x is less than 1. Okay, so we've got a hole, and it goes there. And if x is greater than 1, not including 1, it is a square root function up to 1 to the right. And it is not included. Okay. All right. You can draw yours better. But more or less, there is our function. This graph is not continuous. It is defined, however, and we're going to be having a look at that limit as we approach from the right and from the left. So the first one was, sorry, I'm going to get there from here. The first one was continuous and defined and has a limit at x equals 2. You can see that it approaches the same value from the right and from the left. The second one was not continuous and not defined at x equals 1, but it did have a limit. As you approach from the right and from the left, it does approach a value of 2. Limit approaches 2. The last one was not continuous, but was defined, but had no limit. If you look coming from the right, it looks like that function is approaching a value of 2. If you look coming from the left, it looks like that function is approaching a value of 0. Since the limits are not consistent from the left and from the right, there is no limit. Okay, let's determine the following limits. We've eyeballed them. Let's actually do them. So since this first function was defined and continuous, we can do direct substitution. I don't know if you want to write that down or not. But if I put a 2 into that function, I am going to get a value of 3. So I'm going to write it down. Since the graph is defined and continuous, let's put that in red for danger. We can do direct substitution. That is always the easiest. Please don't forget to try that. Okay. The second one. There is a limit. We saw it. We would like to be able to figure it out. So right now, if I put a 1 in for x, I have a 0 over 0 problem, just like we did with the limits of the tangents. So I can't do that. I've got to use my algebra skills. So my limit as x approaches 1 for, well, I could factor, which is what we did when we drew it. I've got x plus 1 over x minus 1. X minus 1 is the limit as x approaches 1 for x plus 1. I have divided out factors of x minus 1 and x minus 1, which gets rid of the 0 over 0 problem, which is also what the function looks like, by the way. If I substitute my 1 right now, I have a value of 2. We happen to know that there's a hole there, but the limit exists. Graphically, it's because it approaches the same value from the left and from the right limit, but it does approach 2 from both sides. That's the big idea. Okay, and the last one. This piecewise. For the piecewise, if we are approaching the value of 1, which is where it was defined differently, if I'm coming from the left, I am using this piece of the function. And if I do a direct substitution, I get a value of 0. For the right side limit, as we come in from the right, we were on the curve because it was defined that way. And if I do a direct substitution, I end up with a value of 2. We can see that the limit coming from the left and coming from the right has a different value. So this does not have a limit. And we could see that graphically. It was undefined, it was discontinuous, and there was no common value.